Hello, my presentation is titled Influence of GAN cap layer on the threshold voltage in GAN-ALGAN-GAN HEMT. The present paper proposes a theoretical model of threshold voltage for GAN-ALGAN-GAN HEMT. We investigate the influence of GAN capping layer on the structure GAN-ALGAN-GAN. Our results indicate that the threshold voltage VTH decreases to more negative values when increasing the GAN cap doping density N cap or the GAN cap layer thickness. Trinitride-based HEMTs like ALGAN-GAN shown in excellent performance for high frequency and high power microwave applications. At the ALGAN-GAN interface occur a positive net charge plus sigma leading to the formation of the duct in the GAN. In this work, we studied the effect of the GAN cap layer on the electric properties such as threshold voltage and sheet carrier density for GAN-ALGAN-GAN HEMT structure, taking into account the effect of spontaneous and piezoelectric polarization at heterointerface. A simple analytical model for the threshold voltage of GAN-ALGAN-GAN HEMT is proposed by solving one-dimensional Poisson equation to investigate the effects of a GAN capping layer on the structure GAN-ALGAN-GAN. Our device structure is shown in figure 1. The two-duct channel appears at the interface between the buffer layer and the undoped ALGAN spacer layer. In figure 2, the GAN cap layer on top of the electrostructure rises the conduction band and produces a large enhancement in effective barrier height. This is due to a negative polarization charge, minus sigma, at the upper interface, which increases the electric field in the barrier layer and hence decreases the two-duct density. At this point, a two-dimensional whole gas DHG is formed at the upper GAN-ALGAN interface. With an in-place GAN cap layer, the dependence of VTH aluminum mole fraction, including the effects of both spontaneous and piezoelectric charge polarization, is given by the following expression. The sheet carrier density NS under strong inversion region in the channel formed at the ALGAN-GAN interface, the total polarization P and at the upper interface of the heterostructure, the charge density is given by the following expression. In our result, the variation of threshold voltage VTH as a function of barrier ALGAN thickness is shown in figure 3. VTH decreases to more negative values for thicker barrier ALGAN thickness. Figure 4 shows the shear carrier density NS versus VGS for different thickness of N-place doped GAN cap layer. NS increases almost linearly with VGS over a given threshold. Moreover, the curves shift to more negative VGS when increasing the N-place doped GAN cap layer thickness. In figure 5, the variation of sheet carrier density NS is plotted versus the cap layer doping density N cap. As expected, it increases proportionally to N cap. Moreover, the variation is stronger when increasing the cap thickness, typically with 5 nanometers cap thickness. As already anticipated from the preceding result, the threshold voltage VTH decreased to more negative value when increasing either N cap or the GAN cap layer thickness. In this work, we have presented an analytical model for the threshold voltage of GAN-ALGAN-GAN HEMT. Our results indicate that the deposition of a non-doped GAN cap layer on top of ALGAN-GAN reduces the electronic sheet density proportionally to the cap layer thickness. The variation of threshold voltage VTH decreases to more negative values when the in-place doped GaN coupler become thicker. Thank you for your attention.